Hello, everyone. Today, my talk is titled Investigating Language Model Capabilities to Represent and Process Formal Knowledge, a Preliminary Study in Ontology Engineering. I will first start by framing the talk in the context of my work, after which I'll talk a little bit about the motivation for this presentation, and then I'll present the methodology, the experimental setup, and the findings for this experiment. So just to give a little bit of context for this particular talk, it's framed within my PhD research, which is to find neurosymbolic method and to try to integrate neurosymbolic methods to make language models try to reason a little bit better. And of course, I use the word reasoning loosely, specifically in the context of bootstrapping ontology engineering, which means to try to make the process of creating ontologies and specifically of extending ontologies a little bit better. This is a joint PhD effort between Data Science Tech Institute, also known as DSTI, where I teach, and Inria, specifically the Wimmics team. And the work is supervised by Fabien Gondon, Catherine Faron, and Pierre Monin. The goal, the ultimate goal of the research is to try to make language models a better interface and better assistance for human ontologists. And that is because currently we have some limitations, most notably in ontology engineering and ontology extension, which remains a very manual and time-consuming task. Natural language today, the main way of using language models is still a very ambiguous and loose way to exchange information. And language models are known today to hallucinate and to be black boxes, which are two also major drawbacks or at least limitations of this technology. So the work tries to tackle a little bit these different limitations. The main motivation of the overall research is to try to, as much as possible, use symbolic methods to leverage language models a little bit better and to specifically combine them with existing knowledge that language models might have in order to better serve ontology engineering. Try to make language models better and more reliable assistants for human ontologists, and of course, ultimately try to make language models explain their choices when it comes to designing or extending ontologies. A little personal extra motivation for the work is to start with small language models, which are trending again and which are frugal. So they're much more easy to start with, and they might still have some hidden potential that we might have overlooked while scaling into bigger language models. In terms of research questions, what does the work aim to answer? Research question 1, which will be the focus of today's talk: how do different formal representations affect language model reasoning? If we present a problem, and here we're specifically targeting logical problems, first order logic problems. If we present a logic problem in different manners, in different languages to a language model, does it affect the way a language model thinks about the problem or solves the problem? Which leads us to research question 2. Can language models effectively use formal representations, so something other than natural language, to actually better understand how an ontology is created and maybe be able to extend it? And finally, can language models reach to a point where they can explain any kind of choices they make on an ontology, for example, adding a new class, using some known logical tools like syllogistic reasoning? In terms of the proposed approach, the presentation centers around an experimental setup that aims to identify any kind of viable formal language as an alternative to natural language to interface with language models. So this is the first big barrier out of the current constraints that we face with language models. Everything we give them is mainly a natural language. Natural language is loose, ambiguous. What happens if we try to formalize a little bit more our inputs? And this is why the entry point to the work is specifically handling logic problems, because they are very formal problems. Can we, from these results, probably in some future work, extend the usage of some formal representation to better encode information and language models and leverage this information more effectively on ontological tasks? Can we find any kind of evaluation method to evaluate anything that is language model generated in ontologies? Namely, how do we evaluate what models generate to complete, to extend an ontology in terms of classes and properties? And the last point, which is also very important and deals with explainability, how can we use logical tools like syllogisms or syllogistic reasonings, which are a known form of reasoning, to make language models explain their decisions. With that, and without further ado, we introduce a pipeline, a framework, which is called the Syllogistic Evaluation Framework Common Logic Grammar Construction Pipeline. That's a mouthful, so from now on, I'll say CEF-CLGC. This is a pipeline that has two parts. The first part is the CEF part, so it allows to automatically tag or classify a logic problem into a category of syllogism. It builds on previous research that has been proposed by Google to categorize syllogisms to be able to better identify them and to better identify different types of reasoning. And the second part, the CLGC part, is an automatic pipeline to be able to generate formal languages or known logic languages, known and unknown, because we can even do it for custom languages, as we will see, from some basic logical language. And in this case, the entry point is always going to be full. So first order logic language. Such translation or such automatic transformation does not exist today and is not something very easy to do when going from one language to another. The end goal is to be able to evaluate how different forms of representations on a logical input affects the way a language model treats a logical problem. In terms of the formal languages that have been targeted in the context of our experimentation, we've based ourselves on four criteria in order to identify some viable languages. The first being verbosity. We tried to select formal languages that are compact versus verbose in terms of syntax. Frequency, so languages that are either frequently seen by a language model during their initial pre-training. For example, we can imagine that the standard language models that we know today have seen some full representation of problems versus some more obscure formal languages that these language models may have not encountered at all or rarely encountered during pre-training. The third criteria is abstractness. We've experimented with formal languages that are very close to natural language, that are very human readable, versus more abstract, more mathematical formal languages that stray away from natural language to see how a language model handles them. And finally, representation. We've tried to ensure that any language, any formal language that we manipulate in the context of this experiment is finite or has a finite vocabulary or syntax, and that makes the translation in the CLGC pipeline from full much easier, or a little more easy at least. I've shared some examples of what the CEF classification can do. So we've settled on four big categories of syllogisms based on some simple rules to identify them from a logical problem which is by definition constituted of premises and one or more conclusions. We've settled on four syllogistic classes. What we call disjunctive syllogisms are syllogisms that contain a disjunction. Hypothetical syllogisms are syllogisms that contain an implication in either the premise or the conclusion. Categorical syllogism are the famous Aristotelian syllogisms, which consist of two premises and one conclusion exactly that follows from them or does not. And finally, any other kind of syllogism by default will be put in a category called a complex syllogism. So these categories are not final. They are based, of course, on empirical data that we've worked on so far in this experiment, and they are made to probably maybe evolve or expand. In terms of what the CLGC pipeline can do, I've taken a somewhat extreme example to show you what it can generate, starting from a full construction, so a formal language that we humans can read. The CLGC pipeline is going to rely on the BNF grammar representation of this language of full and generate a parse tree of any kind of full input, which is then going to be transformed or mapped into an output parse tree in a target language. In this case, I've chosen a very abstract language, which is TFL plus, that has been introduced by Summers and Engelstein. And this generated tree is going to be validated on the output BNF grammar representation of the target language. It will then be formatted in some formatting function, and it will give an output that looks like an output in a target formal language. So this is how the pipeline operates to move from full to any other logical language that we choose, provided, of course, that we have the BNF grammar of this language, hence the finiteness criterion that was part of our language selection. This is a table that shows some example transformations and also gives you an idea of the weirdness maybe of the languages that we've used, of some of the languages that we've used. I'll start from right to left, from most abstract to probably least abstract. So full is always the entry point. TFL and TFL plus are mathematical logical languages that aim to represent logic or logical problems as much as possible using math. So existential and universal quantifiers are replaced by minuses and pluses. Predicates are just replaced by capital letters. And you can see that it's a very minimalistic, compact, and very mathematical, so abstract language. CLIF and CGIF are two known formal languages that belong to the common logic family of languages that has been advanced and introduced by John Sowa, and he has been one of the inspirations for the naming of the pipeline, so the common logic grammar construction pipeline, since these were two of the first languages that we experimented with. And finally, we've also experimented with our own made up language that we called Miniful, because we wanted to see if we change slightly the syntax of full, which we suppose that language models know a little bit at least, what kind of effect would that have on the learning? And Miniful operates very simply by just replacing the existential and the universal quantifiers of full by words, so all and some, and by replacing the operators, the logical operators, by their binary equivalent. So here, the conjunction with the logical and. In terms of experimental setup, all experiments in the context of this presentation have been carried out on the Folio dataset. The Folio dataset is one of the most well-known natural language full dual datasets consisting of n premises with m conclusions in natural language and full. So this is what makes it interesting, because it gives us the two entry points, the natural language, which language models like, and the full logical formal equivalent, which we want as the input to be able to do our transformations and to generate other languages. It's one of the few languages that, it's one of the few data sets, sorry, that contains both natural language and full equivalence of logical problems, and it's manually curated by humans, so it's validated. The goal of the initial experiments done on this dataset is to predict if the conclusion is true, false, or uncertain based on the premises. So it's a purely reasoning dataset. And for our experimental setup, we've used the Folio dataset and split it into a fixed train, test, and validation split to make it easier to benchmark. And we've run a set of variations of different language models, still trying to stay in the scope of small language models, and different formal languages to see how they affect or impact the output of the language model, and different learning methods. In terms of learning methods, we've used the traditional supervised fine-tuning method, the zero-shot and the few-shot prompting as well, to be able to have a benchmark on prompting. And the aim of the experiment was to try to answer these sub-research questions. Which training method today gives the best results in terms of solving logical problems we will have to deal with at some point for bigger and more challenging reasoning tasks, especially those involving heavy ontologies in the context of the continuation of this work. And the last question, what happens when we have more compact formal languages, like, for example, TFL+, the very mathematical language? How does it affect the performance of language models when the vocabulary of the language is really very small? We've also introduced some additional configurations to our experiments, namely two. The first being in-context grammar passing, which I will refer to as ICGP, which consists in some of our runs introducing the BNF grammar of the language that the problem is translated into as an additional input to the language models to see if this helps maybe the language model understand the language better and probably perform better on the problem itself. And the second is tokenizer retraining, which is to take the tokenizer of the language model and retrain it on the entire folio data set, translate it into one of the formal languages, for example, CLIF, in order for the language model to at least see traces of the language that the problem is going to be framed in. And based on that, we've also had or split our runs in two. Half of the runs had the tokenizer resized to eliminate all existing tokens that the language model knew from its pre-training, keeping to a minimum some tokens that it needs in addition to the vocabulary that it learned from the target language. And the other half of the runs had their tokenizer vocabulary extended with the new tokens that come with the new formal language that the language model was learned on. To give you a small example of ICGP, so in-context grammar passing, in terms of prompting, in our prompting strategies for zero-shot and few-shot, our basic prompts contained the premises and the conclusion of a logical problem to pass to the language model. With the in-context grammar passing, we passed the grammar as an additional input to tell the language model to refer to the BNF grammar to decipher the language that it is reading the problem in before solving it. Now for the results. First of all, in terms of supervised learning, the benchmark and the current state of the art is the natural language, of course. You can see that on the folio data set in terms of this kind of reasoning. The language models perform with an accuracy of 66%. In terms of formal languages, no formal language can outperform natural language, but we have an interesting result where we have languages like CLIF, which are formal but still human readable and kind of close to full, that perform quite close. CLIF is actually the only formal language that is able to break the 60% accuracy and F1 score on the folio dataset for the reasoning task outside of natural language. So hypothetically, it might serve as a viable alternative for natural language. Of course, with a little performance trade-off, but this is to be confirmed with more extensive experiments on other data sets. But it already identifies at least one formal language as a viable alternative to natural language. The second, more subtle result to keep in mind from here is that all formal languages, when we scale the models, so when we move, from example, from a FLAN T5 base to a FLAN T5 large, all formal languages get an increase in performance. So they seem to be able to scale consistently with the scaling of the model, which is something that is not always very obvious or taken for granted, because sometimes when models scale, their learning breaks down. In terms of zero-shot and few-shot results, the results are less impressive in both cases. So in both big learning methods, all models perform worse than in the supervised fine-tuning case, noting that the models here are bigger. So we've experimented with the Gemma 2 billion, which is quite bigger than the FLAN T5 family. So the FLAN-T5 large, the biggest one in supervised fine-tuning being around 700 million parameters, Gemma being in the 2 billion. The noteworthy results here are what happens when we apply grammar prompting. So when we pass the BNF grammar of the target language in the prompt, it does boost the performance in the zero-shot case. It does nothing in the few-shot case. And we still see the same trend of the languages, of the formal languages performance, keeping the same kind of structure or performance magnitude that we've seen in supervised fine-tuning. With that, I mean that Cliff still outperforms everyone else. TFL comes a little bit after it, and Minifol, our own language, which you don't see here, actually performed very, very poorly. So was not even mentioned in the best results. In terms of in-context grammar passing, since we had encouraging results in the zero-shot case, we tried to apply it in the supervised fine-tuning case. So we tried to also pass the BNF grammar of the languages, of the formal languages that we used, on top of the premises as the input, on top of the premises and the conclusion as the input to the supervised fine-tuning methodology. However, we can see that in the case of supervised fine-tuning, we have the reverse effect. Passing the BNF grammar of a language actually hinders the performance, which might seem a little bit counterintuitive at first because it's as if you're passing the translation of a movie along with the movie itself, but it seems to bother the language models more than anything else. So we have actually worse performances with in-context grammar passing than without in-context grammar passing. The other big configuration that we introduced, which is tokenizer retraining, also gave us interesting results. When we retrained and resized the tokenizer of language models to fit a specific formal language, we did get some good performances at a very small scale. And when I say at a small scale, I'm talking about something like FLAN-T5 small, where TFL plus gives an accuracy of 45%. Just for reference, the natural language for FLAN-T5 small gives an accuracy of around 42%. So actually here we break the benchmark, we break the state of the art at a small scale. However, when we scale, so when we move from a very small model to a bigger model, so when we jump from T5 small to T5 base, you can see that the learning collapses and the results actually stop outperforming the state of the art. And this is reflected, for example, in TFL, where for FLAN large, we were supposed to have something that competes with the natural language benchmark, which is around 66%, but you can see that we fall very far from that. So this method actually works at a very, very small scale, but the moment we start scaling models, it seems that the results break down, probably because the architecture of the model becomes too complex for the tokenizer that has been resized on small vocabularies. One last thing that we wanted to provide was the quantitative performance, or one view of the quantitative performance of the best languages. So the top three were obviously the natural language, Cliff, which is a close second, and TFL plus, which ranked third. So it ranked better than even FOL, first order logic. And we wanted to provide a quantitative performance on the different classes or categories of syllogisms on Folio. By scanning the table, we can see that the three kinds of languages or of input representations have similar patterns of performance, which means that they perform quite well on hypothetical and disjunctive syllogisms. They perform equally well on complex syllogisms as well, so they make almost the same number of mistakes, and categorical syllogisms, which unfortunately were very few in the Folio dataset, they had mixed performances in all cases. This makes us speculate or hypothesize that probably, since the performance is maintained by going from one language to another, we can probably imagine arriving to a point where we can substitute natural language with a more formal, rigid language. Of course, there will be some performance trade-off. At least this is what we've seen in the context of our current experiments. And we are currently working on extending the experiments to more logical languages, namely languages deriving from Prolog, for example, to study their effects in the context of the folio dataset, as well as on other dataset that you are identifying. Findings. So if I go back to our 3 questions for this experiment, which training method gives us the best results for solving reasoning tasks that are based on logic problems till now? And in the context of this experimentation, we see that supervised fine-tuning remains the best training method. It is much more stable than anything we've seen with zero-shot and few-shot prompting in our experimental setup. How do formal representations scale with models? Actually, formal languages scale very well with models. This is encouraging because when we can test different formal languages at a very small scale, even if we don't have the possibility to run them at a much bigger scale, we can at least know that we can extrapolate the performance one way or another. So there seems to be some kind of pattern to the way language models learn formal languages. And finally, does having a more compact vocabulary positively affect the performance of language models on formal languages? Unfortunately, the answer is no. With tokenizer retraining, by resizing the tokenizer and by trying to make language models get rid of some tokenized symbols or tokenized patterns in favor of new patterns, we see that we get very erratic performances, especially at scale. As I mentioned at the beginning, the context of this experimentation was to try to answer research question 1, or to try to provide a beginning answer to research question 1. How do different formal representations affect language model reasoning? Today, we can say that language models are capable of learning some kind of structure when it comes to handling formal languages. This shows by their ability to scale. So when we move from a smaller model to a bigger model on the same formal language, we do get an improvement in performance. It seems like less verbose and less abstract languages are easier to learn for language models, and this is maybe to be expected since language models have mainly seen natural language. So languages like CLIF and CGIF do quite well. Languages like TFL and TFL+, which are much more obscure, do less well with language models. And out of this particular experiment, we were able to identify a standout formal language, which is CLIF, which was the one that seemed to be able to break a little bit into the benchmarked state-of-the-art results that is set by natural language. Of course, this requires further experimentation to confirm on more data sets. For our part, in terms of contributions, today the Ceph CLGC pipeline is a working pipeline that can even take and handle more formal languages, and we are currently working on expanding the library of languages that it can move to from FOL. In context, grammar passing was an interesting strategy that till today is not very much experimented with, but that we had the chance to also apply to see the effects of giving the grammar as an instruction set to a language model and how it affects the reasoning of the model. And finally, a tokenizer retraining was also another method that we introduced that does not always get a lot of recognition in current research experimentation, but that ultimately showed us how erratic it can be to play around with the language models tokenizer, especially when scaling. Future work will build on this experiment, and this is currently the scope of what we are doing. We're aiming to extend the setup to include more languages, more data sets, which is a little bit more challenging because we do not have a lot of NL full dual data sets that are available. Most of them do have logical problems in one way or another, but they're not always readily available in full. We will try to also maybe augment and enrich the syllogism categories because we aim to use that in the explainable part of our language models when it comes to justifying decisions made on ontologies in the future, and of course, benchmarking on additional data sets in order to confirm whether or not we have a viable formal language that can serve as an alternative input to language models other than natural languages. Thank you for your time and attention.